Welcome to qnawire.
So we have we have a gas steam combined turbine combined cycle here. So in this case, we have a little bit of an interesting feature in that we're sending some of the steam out of the steam turbine into the combustion chamber for reheating, um, which is an interesting little interesting way to do things. So it turns out that the temperature coming in out of here is 550 degrees C, and while it's coming in here is 550, coming in here is 500. So we're actually getting a higher temperature. Um, Basically, we reheated to a higher temperature. Um, Now we could have obviously done a reheat cycle through the heat exchanger too, but we actually ran it through the combustion chamber, which is an interesting choice. Because actually we're basically then taking some of the energy out that would be then flowing into the gas turbine. So I'm not sure exactly if that's a good thing to do or not, but you could obviously do an analysis of that. So let's see here. We have a pressure ratio in the compressor of we have 12 times the pressure here as we do here, and then 12 times the pressure here as we do here. So this is all at atmospheric pressure here. Let's see here. What else do we know? Coming in, we have 310 Kelvin into the compressor. Into the gas turbine, we have 1,400 Kelvin. These are degrees C. High pressure side of the steam cycle, we have 12.5 megapascals. And the reheat pressure is 2.5 megapascals, and the condenser pressure is 10 kilopascals. We're given a mass flow rate of steam of 12 kilograms per second. So that's, I think, everything we can go talk about there. And so we have, let's see here, we have an analysis to do. So on the gas side of things, we can use the charts to get this reduced pressure. This isn't really the classical reduced pressure, because the reduced pressure at atmospheric temperatures should be very small, because the critical pressure is for air is really high. So I don't know what this is, but it's given in the table and we can use it. It's some relative pressure. Maybe I should just call it a relative pressure, because it isn't their reduced pressure. I'm not sure exactly what that number is, but it's in the charts and we can use it, because what we need is use it as a intermediate. So if we know the temperature at the inlet of the compressor, we can get the enthalpy and this relative pressure, and then we can get the relative pressure at the exit of the condenser, because we know the pressure ratio through the condenser. This is 12. So then that relative pressure winds up being 18.66. And from that, we can then look in the table to figure out what the basically use interpolation to figure out what the enthalpy at 8 is. We could also figure out the temperature at 8, which I didn't do, but again, you could figure that out too from the chart. Now at 9, we have 1400 Kelvin, so we can get the enthalpy there. And again, we can get off that same chart the relative pressure. And again, divide this by 12, because again, this pressure ratio. So we have then now we have this relative pressure at 10, so then we get the enthalpy at 10. And that gives us we could also get the temperature at 10, which I didn't do. We know the temperature at 11 is given to us, I think, right? Yeah. And so we can get the enthalpy at 11. Right. So let's see here. Then we have, where did we get the temperature at 11? You tell? You have to heat to oh yeah, 247 C. So I converted that to Kelvin, so we can look it up in the. Oh, we can just look up in the table. What table is that? Just for your reference, it is table. Let's see here. What one table was that? Where is that table? Um, ugh, what table is that? Let me see here. I thought I wrote it down in my note. Oh, it's table A17. So that's where I got that. Now we can go down to the steam side of things. Enthalpy, specific enthalpy, specific volume work done into the pump, specific work into the pump, specific enthalpy out of the pump. Pressure and temperature into the steam turbine, enthalpy and entropy out of the steam turbine, specific values. Isentropic turbine, so we know the pressure coming out of the going into the reheat cycle. So we can get the enthalpy coming out of the turbine, and then we know also the pressure and the temperature coming back into the turbine. And so we can get the enthalpy of the reheated steam coming back into the turbine. And we can also get the entropy there. At 10, we know the pressure, and it's an isentropic turbine again, so we know the entropy. And so we can get the quality factor and the specific enthalpy out of there. Now we have all of our specific enthalpies. So we can look at the heat exchanger. And so this is the change in heat in the steam side, and then change in heat in the gas side, change in basic enthalpy in the gas and the steam side. Those have to be equal. And so we know everything in here but m dot g, and we wind up with m dot g equals 153.9 kilograms per second. Now, we can get the heat in, and that is the heat into the into the gas in the combustion chamber, and then heat into the steam in the combustion chamber also. And so we know, so this we have the mass flow of gas, and then we know this, the mass flow of steam, and we know these two things. So we can figure out that the total heat into the combustion chamber, or basically the heat that we're getting out of the combustion process, is 144 megawatts. Now, that's, so now we get the heat out. So this is the heat out from the gas and the heat out from the steam. So the heat out of the gas that we lost from the gas, again, as it exited the heat exchanger and got back down to the atmospheric conditions. Get that. And then this is the heat out of the condenser in the steam side. So that winds up being 58.9 megawatts. Let's see here. We now know with these two things, we can get the efficiency. It's 1 minus this divided by this, and that winds up being 59.1%.